Assalamualaikum and good day everyone. I hope you are all doing well. So today we are going to continue on our chapter 2 digital image fundamental. Alright, like previously, like I told you before, an image is represented by a pixel where each pixel there are values that represent each of the pixel, okay? Alright, so image is actually represented, or I can say image is composed of row, where is the color marker right now? Is represented by M and also N. Okay, so when you write an image, it is represented by M and N. Okay, so pixel value are mostly often gray levels in the range of 0 to it is actually often gray level, not it is just often, meaning it is not a must. So gray level is actually represented by 0 to 255, where 0 represent a darkest gray, or I can say black, and 1 is the lightest gray, which is of course white, right? Okay, we will see later on that image can easily be represented as matrices. Okay, moving on to the next picture. If you can see in the next picture, it is not actually gray level. Why? Because you can see inside the value here is only 0 and 1. So what actually the format of this image? Okay, this image is, we can say, we call it the binary images. Okay, this is the binary images, where it is represented by 0 and white. Binary images meaning it only have 0 and white. Okay, so that's why the images, when what you can see the value, these images actually represented the images over here. Okay, so binary images, what is really good about binary images is actually you can use binary image to outline information, okay, and also information such as shape, tree, and shape, and many else. Okay, so that is the main application, like why people use binary image sometimes. Okay, so next is, okay, now we have other example of binary images where you can see the value inside here is 0 and 1, and this is actually the value that form this image over here. Okay, alright. Oh, before I forgot, binary images is actually an images created from grayscale images. Okay, so from a grayscale images you can actually convert it to a binary black and white image, or we can say binary image, by using threshold operation. Alright, now moving into our next image, where we have such a handsome eagle there. Okay, so if you see clearly, for this eagle, clearly it's not a binary image because it is not black and white. So for this eagle, we can say it is a grayscale image. Grayscale image, usually we can also call it as monochrome image. Monochrome image, where mono means one. Okay, so it is actually monocolor. Why? Because as we say, it is the one color that it is actually saying is gray, right? Okay, and moreover, what is more special about grayscale images is it contains brightness information. How? As you can see, the gray images is from 0 to 255, where 0 represent the darkest, while the 255 represent the lightest. So from the value itself, you can see that it represents brightness information, right? Light to dark, dark to light. So if you want to study some brightness, some information on brightness of color, brightness, so you better study a grayscale format of the image, okay? Because as you know, there are several formats of an image. Or just now I said there is black and white. Now it is grayscale. And next we have RGB. Okay, RGB, which of course R represent red, G represent green, B represent blue. So actually when we have this color here, when we have a full color of image here, it is actually formed by the pixel representation of red plus pixel representation from green, pixel representation from blue. That's why we obtain this image, this value like this, that represented image over here. Okay, if we say like RGB also, if we represent it in like pixel, we can say it is represented like this, R, G and B. Okay, it's like that. If we have 100% here, meaning it is saturated with red because the first one is red. If we have 100% here, it is saturated with green. If, for example, if I say 50% here, so this image here is, we can say, for example, 0 here, meaning 0 representation of red, 100% representation of green, and 50% of blue. So if by understanding the color, I think we can much imagine the color output, right? Because no red meaning green and also blue, so the color might look something like more to brown color probably. So maybe you can try that out. So the value scale has 256, okay, 256 different values. Each value is a number between 0 and 255, and one needs 8 bits to represent such a number. So therefore 8 plus 8 plus 8 meaning 24 bits to fully represent an RGB color. Okay, so size of a color image, okay, which means so RGB color we should have like this. Size of a color image, we have width plus height plus the 24 bits. This is how you present it. Okay, so for example, if we have a 640 plus 408 and 640 times 480 size of an image, so it takes about 91921,600 bits. Okay, so that is the idea. Sometimes when we have an image, it will involve the memory, right? So this is how, when an image, you can say how the image is too big or the image is too small. This is the color. This is how it is calculated. Okay, so of course, by looking at this, you can say that the color image is consume a larger data compared to the image that we have explained before, which is grayscale and also black and white. Alright, now we have the other example. So I'm so sorry with this mistake. This shouldn't be here. Okay, so for the first image, of course, it is a grayscale image. Grayscale image. I'm sorry for the spelling. Grayscale image. Let me correct that. Grayscale. Okay, which is of course not a black and white. Black and white should be like a very straightforward image, and therefore this is not a black and white image. And the second one is of course an RGB image. And for the final one, you see how come there are another image there. So how can we represent such image like this? So I can say that for a grayscale image, it is one sample per point, meaning if we have like a pixel, right, we have a pixel that represent like a square. So in this value, there should be like a value from 0 to 255. Okay, so for that's why we call it one sample per point. So for an RGB images, for example, like when we have a pixel here, if I brought it out like this, it should be represented by R, G, and B, meaning 3 samples per point. Okay, and as for the third picture, let me give you some clue. It is actually represented by 4 samples per point. How can that be? So it is actually represented by red. Of course, it is a RGB color, right? R, G, and B, and there's actually an extra samples here, where for this example it is alpha, where alpha actually represent an opacity. Okay, all right, so that can happen to an image. So for example, we are going to go to our next example. All right, so for the next example, before we have seen opacity, and now some example, I can assume that it also has noise, and another noise we can say is saturation. Okay, so saturation and noise, saturation is the highest value beyond which all intensity levels are clipped. Note how the entire saturated area, see, note that the entire saturated area has a high constant intensity level. So we will learn more about noise in our next chapter. So I think that's all for today's video. See you all in my next video. Thank you.